So I'm Jackson Stansell. As Bryce mentioned, I'm the founder and CEO of Sentinel Ag. And what I'm here to talk to you a little bit about today is better nitrogen management. And specifically, I'm going to start out with talking about nitrogen management with manure, some of the challenges that are there agronomically. I'll touch a little bit on nutrient management plans with a specific focus on BMPs for nitrogen management. We're going to talk about determining agronomic nitrogen rates, which is critical to what we do, but also critical to success with these nutrient management plans. And then really the core of the presentation is going to focus on justifying crop appropriate amounts of nitrogen. I think there's a huge opportunity in this space. And the message I really want to leave with y'all today is the way that I see it. As dairies, y'all are constrained in terms of what you can do with nitrogen management, and it's really quite limiting. And so I want to make sure that you're aware of the tools that are available to help you meet the agronomic needs of the crop, be able to better allocate the waste that is on the operation, and take advantage of all the benefits that can come from that, but also keep you within the bounds of these nutrient management plans. We'll focus a lot on in-season crop nitrogen tracking as one of these tools that can be used to justify applying crop appropriate amounts of nitrogen. And then finally, we'll get into some future opportunities and needs. So to start out with talking about the agronomy challenge of nitrogen, one of the things that I always like to highlight is that nitrogen is really a very complex system. There are a ton of different factors that influence how nitrogen becomes available to crops in the field. And really one of the biggest challenges with nitrogen, unlike water and some other nutrients and other things that go into crop production, is that nitrogen transformations are largely invisible. You cannot see what is going on under the ground. You really can't see nitrogen when it is in plant available form, which makes it really hard to manage. There are a ton of different conversion pathways that nitrogen can go through, from volatilization to nitrification, denitrification, mineralization. There are a ton of different pathways, and they're all really controlled by moisture, temperature, pH, forms of nitrogen as it goes into the soil, and also biological activity. So there are all these different things that can affect how nitrogen is working in the environment. When you start talking about nitrogen management with manure, you start to add even more complexity to this system because there is so much variation in the forms of nitrogen within manure. So if you look at this graph here that comes from the University of Minnesota, breaking down inorganic versus organic nitrogen sources within manure, you can see that there's a ton of variability based on the origination source of that manure. Dairy and beef are kind of in the mid 50% for liquid manure in terms of composition for both inorganic and organic nitrogen. And as you get into solid manure, the fraction of organic nitrogen really starts to take over, right? You really reduce that inorganic fraction within the manure. Composition of manure can also vary a lot by time and where you're pulling that source from, what time you're pulling that source, right? And so there's a lot of variation here just in manure composition that needs to be thought about when you're looking at nitrogen conversion. From a manure availability standpoint, there are also a lot of concerns. So as we talk about that inorganic versus organic fraction of nitrogen in manure, when we're talking about inorganic nitrogen, what we're mostly talking about is plant available nitrogen, right? There are two primary sources. There's ammonium, which is positively charged, and there's nitrate, which is negatively charged. Soils do not do a very good job of holding on to negative charges, right? So that nitrate form is what is going to be the most mobile within your soil solution. It's also the form that plants want to uptake the most, especially early on in the growing season, right? So it's important to have nitrogen in this form, but it's also risky to have nitrogen in this form. Organic nitrogen is largely carbon linked, so it's not going to be floating out there in the soil solution. It has to go through a process called mineralization, which I'll talk about here in a minute, to actually convert into those plant available forms. But that's also really critical to consider when you're thinking about the nitrogen that's coming from manure as a source. This table over here on the right shows basically the fraction of that organic nitrogen that is typically thought to be available by time after manure application. In most cases, when you're dealing with dairy and with liquid slurries, you're looking at about 40% that's estimated to be available in the first year from that nitrogen. The rest of that is going to become available over subsequent years of conversion with that source sitting in the field. Those are estimates, and in my experience with nitrogen, mineralization is extremely variable from year to year. So you really, yes, you may be thinking that you're going to get 40%. It may be a lot more than that. It could even be less than that, depending on what the environmental conditions are that you're given and exactly what your soil composition is. Mineralization is basically the conversion of a nutrient from an organic form, so again, that carbon-linked form of the nutrient, into a plant-available form that plants can use. Biological activity in the soil is extremely impactful on mineralization, as is soil temperature, soil moisture, pH, and also the incorporation of that original source and the depth at which this is all happening, right? So there are, again, a ton of factors that are happening here. If you look at these two graphs that are on this screen, what you can see here is that soil moisture has a huge impact on the relative mineralization rate. So the drier your soil is, the less you're going to be able to mineralize. The closer you are to field capacity, the more at peak mineralization you're going to be. But as you get into saturated soil conditions, so if you're maintaining soil moisture above field capacity, you actually start to hurt your mineralization rate again, and you actually move into more of a denitrification mechanism where you're going to be losing nitrogen and it's not going to be in a plant available form. Plus, your roots really aren't able to access and your plants aren't able to utilize what's in the soil because they're losing oxygen as that pore space is taken up. So soil moisture management is really critical to maximizing mineralization. The more optimal your conditions are, the more mineralization you're going to get during a growing season, and that may drive that fraction beyond 40% in terms of first year manure nitrogen conversion. As you look at soil temperature, the story here is similar, but also different. You don't really have a point until you get into very, very extreme temperatures, which we're not going to find within the natural environment, where you are starting to limit mineralization based on temperature. So really, as temperature goes up, it's kind of like being in an oven or something like that, right? You're going to be cooking that organic matter and turning it into plant available nitrogen. So this is really what's going on when you think about manure turning into plant available nitrogen in the soil. From there, as you have this plant available ammonium and nitrate that's in the soil from manure, there's also a process called nitrification that is ongoing in the soil. And this is a conversion from ammonium to nitrate. Remember, the nitrate is not held onto very well by the soil. This again is driven by temperature, moisture, and pH. But ultimately, this process is what both makes nitrogen available, but also puts it at risk. Nitrate can stay in the soil, but largely it moves like water does in the soil. So if you have a large rainfall event, if you have excessive irrigations, you have anything in that category, this nitrate is susceptible to moving through the soil profile and being past where roots can access it. So it's really important to manage the nitrate concentration in your soil very carefully. Similar to mineralization, you actually have very similar dynamics. At field capacity for soil moisture, so this is basically the optimal amount of water that your soil can hold, you're actually going to get the highest rate of nitrification. So just like you're mineralizing at the highest rate, you're also converting to nitrate at the highest rate. That means if you get a rainfall event that pushes you past field capacity to saturation, you're at risk of driving that nitrate past where the roots can access it. So it's really, really important to think about your soil moisture and how you're managing that. Again, temperature and pH drive this. The warmer it gets, the more nitrate you're converting, okay? There are some really beneficial aspects of all these processes that we can use and think about when we're talking about managing nitrogen in season, which I'll get to later. That's really why I want to talk about some of these factors. The last one that I will talk about on this baseline agronomy side of managing nitrogen with manure is denitrification. And so this is the process of converting that nitrate in very saturated, heavy textured soils into nitrogen gas that is basically going to come off of the surface and is going to lose that nitrogen so it's not available to the plant to use any longer. This particular process is one of the biggest things when you talk about climate smart ag and the carbon intensity of crops. This nitrous oxide gas is a greenhouse gas and it counts against you from a carbon intensity standpoint. So for any of you that are thinking about that or the downstream impacts of carbon intensity of grain that's going into feed for eventual milk, right? This is something that you may want to consider when we look at whole life cycle analysis. The prime conditions here, again, are low hydraulic conductivity soils, so very heavy soil textures where you're going to get ponding, warm conditions, high water tables. I know some of you may not be dealing with these conditions if you're in sandy soils, but it is something to definitely consider, especially in those lower spots in the field. So in summary, manure nitrogen management is difficult, and What I really want to leave you with from an agronomy perspective here is there are a lot of processes that are happening. They're happening mostly during the season as your crop is growing. And so predetermining your nitrogen needs is really about as difficult as predetermining how much water your crop is going to need during the season if you're irrigating, and basically forecasting out the amount and timing of rainfalls throughout the growing season. It's really difficult to do. A lot of y'all would tell me that I'm crazy if I told you were going to do that with irrigation. It's kind of the same thing with nitrogen, right? It's really, really difficult to predict exactly how much nitrogen your crop is going to need. So as we get into nutrient management planning, there are, from my perspective, reading different nutrient management planning documents around the US, there are kind of 6 different categories that most nutrient management plans involve. This is an example of just the Georgia Department of Agriculture Nutrient Management Plan checklist. And really what I'm going to focus on for the rest of the presentation is land-based and land characterization and some of those impacts on making in-season nitrogen management decisions. I'm going to focus a lot on testing and baseline data. So how do we actually inform what we're doing from an application standpoint? I'm going to talk a lot about nutrient budgets and application plans, and then finally about record keeping and accountability. So those are kind of the 4 areas that the rest of this conversation is going to focus on. As we look at these nutrient management plans, the 4 R's are everywhere. To be honest, I get kind of sick about talking about the 4 R's because I think there's a lot of nuance that goes into the 4 R's. And there needs to be a lot more detail than just right rate, right time, right place, right source. But it is still a pretty good framework for talking about nitrogen management. When it comes to right rate for nutrient management plans, university recommendations seem to be the most common basis for determining those agronomically appropriate nitrogen rates. Most universities provide a total nitrogen limit. There are some that also break this into individual manure nitrogen limits as well. I know Minnesota is one of those that actually has a particular manure nitrogen cutoff, right? And there's additional room above that for total nitrogen, but this really varies state to state. Right time is really, really important. I think this is almost as important as rate in many ways from what we've seen in our research. And this is really about aligning the availability of nutrients with when the crop is actually going to take those nutrients up. Right place and right source are also important. I don't think they're as important as the first 2. Right place can be if you're in a situation where you have a ton of in-field variability. We don't always have that condition, right? There are fields that are uniform enough that you can treat the same way and really get the benefits from. Some are not so much in that position. Right source is important. It's really about making sure that the nutrients that are in the source are going to be available when your crop needs them, and that's really all that boils down to. So I want to focus a little bit more on this agronomic nitrogen rate concept. And what I've done is I've pulled 3 different states and their agronomic rate definition to give you a little bit of an example. If your state is not included, I'll tell you Georgia, I'll talk about at the very end here. So Georgia will not be included in these first 3, but if your state is not included, doesn't mean I don't think it's important. I just think these are 3 really good examples of how this is defined around the US. So in Minnesota, I'm going to read just the bulleted here. Nitrogen application rates should be consistent with the appropriate University of Minnesota maximum return to nitrogen value. So they're using an MRTN approach to determine what the agronomically appropriate nitrogen rate should be. This basically takes into account crop price, nitrogen cost, and agronomics to set a value for the total amount of nitrogen that is recommended. What Minnesota is moving to, and we're seeing this with the Minnesota Department of Ag, is they're moving in the direction, especially in areas that are having water quality concerns, that they're going to require the use of alternative management tools, right? So they're looking for other ways of determining this agronomically appropriate nitrogen rate because with their current approaches, they're not seeing success in controlling groundwater and surface water nitrate, right? And this is especially driven south of Minneapolis, where you're starting to get more pressure from urban centers. And so these level 3 areas are moving towards requiring the use of alternative management tools. In Wisconsin, their state level standards are largely focused on NRCS alignment. And in general, they have a University of Wisconsin extension publication that defines the agronomically appropriate nitrogen rate for corn, for example, or other crops. But they also have kind of a clause in their policy that says up to 46 pounds per acre of nitrogen per season of supplemental nitrogen can be applied in the case of need of a rescue nitrogen application. This has to be documented using guidelines for adaptive nutrient management. They have a whole other technical section, so much paperwork to work through, but you have to use 2 different methods in order to justify applying more than 46 pounds of nitrogen per acre during the season, right? So what their approach is looking at least having one method to justify applications up to 46 pounds of nitrogen per acre, and if you need to go over that, you have to have 2 methods of justification to document this in Wisconsin. With Florida, it's a very similar definition. Supplemental application may be justified based on tissue testing, cultivar-specific requirements, other technological or testing methods, or substantiated production data that demonstrates crop needs. So I want you to remember those 3 definitions, and I'm going to talk a little bit about in-season nitrogen management and aligning with crop utilization, because this is important. If you lose nitrogen during the season, or you do not have enough nitrogen out there to meet yield potential, you are going to need to make a supplemental application in season to make sure that you're achieving that yield potential. What's also important to consider is when the crop is going to be utilizing nitrogen, so that you can either build this into your plan in the first place, or at least be aware of how that crop is going to be maybe in a nitrogen deficit after a nitrogen loss event. With corn specifically, you're looking at having about 33%, so 1/3 of all total nitrogen uptake after R1. So this is after corn is pollinated, during pollination really, and heading into the grain field period. Another 1/3 of that is going to happen just before that, from V12 to R1. We'll have roughly 24 to 25% that's happening from V6 to V12. We're really building the biomass out there in the field, and only about 10% of that uptake happens before V6. So anything that we're doing prior to V6, as far as a nutrient application, either needs to be in the form of a nutrient that's not converting to an unstable form out there that's susceptible to loss, right? Or it needs to be an application that is geared towards having that nutrient become available later in the season when the bulk of nitrogen uptake, 90% of nitrogen uptake, is going to occur. We do have some things working for us, especially when it comes to manure nitrogen management with mineralization in the field. So mineralization generally will increase over the course of this timeline. So we're generally planting in cooler conditions than the crop is in when it is in the mid-vegetative and reproductive stages, right? So mineralization is increasing there too. Mineralization will naturally supply some of this in-season nitrogen need. We don't know how much, but that's going to be happening. It's also important to see that there's a little bit of an inflection point in nitrogen uptake that occurs around R3. So this is as the crop is really starting to finish out. What we really need to understand if we're going to produce and get to our yield potential that is most profitable for us, we really need to understand this inflection point and how mineralization is interacting at this inflection point to continue supplying the crop with the nitrogen that it needs. This is corn, but this is really pretty much true for any sort of grain crop out there. Any sort of grass crop will follow the same basic curve with some slightly different partitioning in that nitrogen utilization across the season. From a seasonal variability standpoint, this is also something that I want to highlight, and this is coming from the University of Georgia. In consecutive growing seasons, they observed a 24-day difference between growth stages in consecutive years. If you think about 24 days in terms of the rainfall events that can occur there, the accumulation of GDDs, how that biomass is building, that is a lot of time for difference in nitrogen utilization, availability, and loss mechanisms. So if you're on roughly the same application schedule that you've always been, that application schedule may not be interacting appropriately with how that crop is changing year to year. There also is likely a difference in yield potential. If there's a 24-day difference in crop growth stage development, we may be getting into warmer weather when that crop is getting into the later growth stages. That may impact it as well. So how does this really change the total nitrogen need and timing? So as we think about the in-season nitrogen dynamics of corn and some of these state definitions, what we're starting to see is a bit of a convergence in approaches across different states around how to create these agronomic nitrogen rates and also how to justify in-season applications. These are just some words that I read as I was looking at these different state level definitions, and justify was really the biggest word that popped up in multiple different definitions. So what I believe is that agile nitrogen stewardship is needed in order to get us past this predictive pre-plant agronomic nitrogen rate recommendation that really poorly predicts total nitrogen needs. Across different state definitions, there are basically 4 different methods that are accepted for justification. There are soil nitrate tests, plant tissue tests, sensors, and models. The state of Wisconsin has basically these listed out within their definitions, so they're a really good source to go and look at in terms of the definitions. I'll briefly cover each one of these. With soil nitrate tests, what you're really doing is you're assessing the nitrate that is existent in the soil just prior to a side dress application. Some of the pros of this is that you're actually getting a measurement of soil available nitrogen. There's a very low barrier to entry. You don't have to do a whole lot other than pull a soil sample, send it to a lab, and get the number back. And it fits really easily into a lot of these university algorithms because a lot of them are built to use a soil nitrate value in making a rate recommendation. Some of the disadvantages are that this is a very labor-intensive process. It is pretty spatially dismissive because nobody, at least nobody that I know, is going to go out and pull a grid soil sample while the crop is growing actively in the field. And so you're not going to get a full understanding of the spatial needs within the field. And you're really only assessing nitrates. So you're not actually even looking at what is that fraction of nitrogen that may become available for the rest of the season. So you're really not taking that into account. So this is really only in extreme loss scenarios where this really has significant applicability. When you look at plant tissue tests as a second methodology for informing these in-season applications and justifying in-season applications, what you're looking at here is basically nitrogen concentration in the plant tissue. What some of the advantages here are is that it actually can reveal the concentrations of multiple different nutrients. So if you're looking for nutritional balance and how that crop is utilizing different nutrients, this can be a really good tool. Again, this is a low barrier to entry. All you really have to do is go pull leaves off of a plant, ship them to the lab, and get a number back. But some of the challenges here, this is slow turnaround time. It can be up to a week before you get results back, so you're really working in arrears in a lot of cases. It's not a predictive system, so it's not going to predict how much nitrogen will be available in the future. It is also spatially dismissive because it is very difficult to go out and pull enough tissue samples in enough different parts of the field to fully understand what is going on. And for the most part, it is not generalized and doesn't fit very easily into these university recommendations. So there's really not a good downstream rate information engine that's been built around plant tissue tests yet. There are some folks that have developed their own ways of determining the appropriate nitrogen rates from these tissue tests, but those are some of the disadvantages to plant tissue testing. Nitrogen models are another thing that can be used to justify these in-season applications. Basically what these nitrogen models are is they're mathematical representations that predict nitrogen availability and uptake under our current and anticipated weather conditions in the field. They're really helpful for getting around atmospheric impedance. So if we have a lot of cloudy weather, these models are pretty much resistant to that. They're able to work all the time. They're always on, so you can get an on-demand recommendation from them. And they are able to help you with prediction. They're models, so they're literally inherently built to be predictive. From a disadvantage standpoint, a lot of models don't really have an in-season calibration component. So they're all based on getting the starting conditions right and hopefully getting all the right measurements from weather stations put into the system in season. And they often have to be recalibrated to every different geography that they go to because they're highly dependent on how those soils are represented and how management practices are done in that particular region. The last one that I'll highlight here is sensor-based algorithms. I am highly biased towards this because this is where a lot of my master's research went. These sensor-based algorithms basically include the measurement and interpretation of crop reflectance data. So this is optical information to assess crop nitrogen status and imminent needs. This is basically how the crop is using light and us measuring how the crop is using light. Some of the advantages to this is that it's very easy to calibrate this sort of information in season to understand how the crop is actually responding to nitrogen. It's a very high resolution data set. It is site specific and it is also specific to individual crop responses. So it can be very hybrid or variety specific. And there is a very high frequency of data collection. The disadvantage here is that it can be impeded by environmental conditions. So if you have cloudy weather, it's going to be very difficult to capture these images. And it does have a little bit of a limitation when it comes to predictivity. So it's hard to forecast out based on this sensor-based information. However, there is a movement within the industry towards having these sensor-based methods be the go-to for agronomic nitrogen rate determination. In the state of Nebraska, actually last year, they just shifted to recommending that irrigated corn growers use sensor-based nitrogen management for their agronomic nitrogen rate determination because of the clear advantages that it has offered from the standpoint of profitability and nitrogen use efficiency. So this is now the Nebraska standard for nitrogen management in the state. What I'll now talk about is sensors have a lot of limitations. They are impeded by atmospheric conditions. That's where models really stand out. And so what we are beginning to do a lot of work on at Sentinel Ag is how do we integrate sensors and models to create a system that really has guaranteed availability and is able to consistently provide all of the data that you need to justify and inform your in-season nitrogen applications. This is an extremely busy slide, and I don't want to go into all of the details here, but what I really want you to pull out of this slide is there's a lot of data that goes into these models. The green rectangles on the left side of your screen, those are the only two pieces of data that really require human input at this point. All other pieces of data in this modeling approach can be automatically sourced from, for example, John Deere Operations Center, from online APIs between sources. This is all automatic and happening in the background. So there's really starting to become a very low manual lift to integrating models into your system. This ultimately gets distilled down into 4 outputs that are very easy to understand and interpret. One is a sufficiency index that actually just tracks the sufficiency of the crop over the growing season. There's near-term and long-term nitrogen demand, and then there are ultimately crop growth metrics as well. So how well are we building biomass? How well are we remobilizing nitrogen? All of these different concepts, but ultimately these data sources get distilled down very easily into primary metrics. And we do believe that this integrated system overcomes some of the challenges of sensors and models and ultimately offers a better and more scalable system for making in-season decisions than plant tissue testing or soil testing alone. Bryce mentioned in my intro that I played football in college, so the way that we think about nitrogen management at Sentinel is largely around the idea of game planning. So when I was playing football, I played tight end and H-back, and going into every game, we had a legal size piece of paper that basically had our script on it for the game. We had all the different play calls that we had prepared for that week. We also had basically our first 2 to 3 drives scripted out for the entire game. We knew exactly which plays we were going to run, and we were going to run those to basically see how the defense was going to set up for us in that particular game. And then we were going to make our reads and ultimately make adjustments to fit to how the defense was playing us in that game. That's exactly how we think about nitrogen, right? So as we go into the season, we have a nitrogen plan that we have prepared that basically gives us our script to operate off of for the season. This is roughly when we expect to time applications, how much we're going to apply at those different times. And so that's going to set our baseline and give us a plan going in. What we believe is very important is to read the actual conditions that you're getting and make the adjustments based on those conditions that ultimately deliver the right outcome. And that's what I'm going to talk about a little bit more now. One thing that is really important to do when you're reading and making those adjustments in season is, number one, detecting nitrogen demand. We've talked about nitrogen concentration in plant tissue being a way to do this. At Sentinel, we offer a sufficiency index concept that actually measures the nitrogen sufficiency of the crop over the course of the growing season using imagery from satellites that's coming in on a near daily basis. We're typically getting about 3 to 4 satellite images per week, so that means that you're going to get 3 to 4 measurements of nitrogen status per week. This is like going to pull out tissue samples 3 to 4 times a week, and we can all think about how labor intensive that would be. This is an example of what that nitrogen sufficiency index time series looks like within the platform. But this sufficiency index, as you can see, tracks down into kind of a yellow region and then ultimately into a red region here. These yellow and red indicators are basically like a stoplight. Red is bad, yellow is it's getting bad, green is good. So we really want to keep everything within this green range because that is going to be the optimal. To show you how this is actually working to indicate the nitrogen sufficiency of the crop, what I've put here are 3 black lines that indicate where applications were made on this particular field. And you can see after each one of these applications, there's a positive response in the sufficiency index. So we know that after that nitrogen was applied, it was making it into the crop and it was actually pushing it closer into the optimal range. What is really important about this is the sufficiency index gives you a number that basically says, and also a status associated with that number that says, do I need more nitrogen on this crop, right? Our belief is that this sort of number fits into many of those state definitions for documentation and justification of additional nitrogen applications if they need to exceed your nutrient management plan, right? So this is a scalable number that can be used to document the rationale for those applications, and also to show the effectiveness of those applications for reaching an intended outcome. And lastly, that no more intervention has been made once that optimal outcome has been reached. So all the decisions that have been made are just in the interest of getting that crop to its optimal outcome or to its yield potential and profit potential. With sensors and modeling, there's also the ability to spatially assess leaching risk. We talked about Wisconsin and how they will often require two methods. They do require two methods of documentation in order to justify applications exceeding 46 pounds of nitrogen per acre. So let's say that you actually have 80 pounds of nitrogen worth of yield potential that you need to go chase in the field. You would have to have two different methods of documentation in Wisconsin. This particular method would be one method of documentation. Leaching risk could be a second method of documentation used to say that we actually do need additional nitrogen in the field. And so what we're now able to do with remote sensing information is track soil moisture and track soil moisture at different depths in the field. The way that this is really working is that satellite information, specifically microwave data, is measuring the soil moisture in the top 2.5 inches of the soil, and a hydrologic model is modeling how that water is propagating down through the soil profile. But with that, and because we can do it spatially, you can actually isolate different areas of the field that may have more or less soil moisture, and in that case, by saying how close they are to field capacity, how prone they are to leaching. So if you get a rainfall event or you had a rainfall event and you see that you have this spatial leaching risk map that says you had a high leaching potential here, there's a very high likelihood of leaching in this particular region. That can be used to drive an in-season justification for applying more nitrogen, possibly beyond that currently allotted limit, if it is agronomically beneficial. We also see some utility here for leveraging the sufficiency index and generally recommendations based on the sufficiency index to select fields for application. So if you have a situation where you need to pump lagoon water out to particular fields, it sometimes can be beneficial to know which fields are in most need of that nitrogen, because if you have a justification, right, as in the sufficiency index, where some metric is saying that you do not have enough nitrogen on this particular field, that can be a justification for sending that lagoon water to that particular field to drive the nitrogen status of that field up into the optimal region, right? So this is another opportunity for how to use the sufficiency index information. This can also be used out of season, right? If we're tracking this sufficiency index over the course of the growing season and we see that there's a field that has a chronic shortage on nitrogen, we can also allocate manure to that particular field out of season as well to build up more of that nutritional profile. There are risks with that. Obviously, if you're converting into nitrate, that's going to be at risk again, and so you might put yourself in a negative situation there, but that's another way that this can be used, and ultimately this can measure the success of applications at scale as well. So if we do allocate lagoon water out to a couple of fields, we can see those fields either recover or not recover based on the application that was made. So that's an important understanding for future decisions as well. This technology can also quantify agronomic nitrogen rates. So there are built-in algorithms, both within the model and based on the sensors, that can determine what the appropriate nitrogen rate is to correct what we are sensing and modeling in the field. This can be done spatially, which I think is a very important factor if you're dealing with highly spatially variable soils. And you can also tailor these recommendations to the goals that you have in your operation. So if your goal is building more biomass, you can prioritize rates that are actually going to build more biomass in the crop in your field. If you're looking for more grain weight, that's also something that can be done with models because they're actually able to forecast out how the crop is going to be building these different components that go into yield and profitability. We also know that manure is variable. And when we're dealing with variable sources, there may be spatial variability in terms of where that nitrogen is coming from a manure application. There are subfield regions that may not have received adequate nitrogen. So another potential possibility here is if you have areas of a field that have not received enough nitrogen, you can allocate potentially some commercial nitrogen fertilizer to just those areas in the field, again, without exceeding the total nutrient management plan for the entire field. So having that sort of spatial look can also give you good opportunities for operating within your nutrient management plan with justification. So lastly, I'll just kind of sum all of this up about maximizing the utility of justification in your operation. Integrated sensing and modeling really provides at least two methods of justification that you can use in one while providing a complete tool to support your decision making in season. What's great about this is sensors are accepted as a justification method, models are accepted as a justification method, and generally a reasonable estimation of leaching is also accepted as a justification method for these in-season applications. So there are at least two, possibly three of these methods that are all coming in one when you talk about an integrated sensing and modeling system. We're not the only ones out there that do this. We're the only ones out there that do it the way that we do it. But there are a lot of different solutions out there for tracking and modeling nitrogen in season. So a few questions I want to leave you with when you think about maximizing the utility of justification is how much commercial nitrogen can you eliminate from your program that will give you a little bit more of an edge when it comes to your nitrogen costs in your operation, potentially utilizing more of the manure that's being created on your operation. Right now, our data suggests about 45 pounds of nitrogen per acre can generally be cut from a commercial nitrogen program, and this is without manure usage. This is largely on silt loam, sandy loam, and silty clay loam soils, so I'm not going to say that this applies to every single soil type, but there really is a lot of data out there that suggests that we're over-applying nitrogen by about 40 to 50 pounds of nitrogen per acre. Second question I'll leave you with is how does reducing commercial nitrogen help you to achieve two objectives? Number one, eliminating cost within your operation, but also number two, giving you more opportunity to use manure and get rid of that waste on your operation. So just maybe think about that question and how that might pertain to you and the goals that you have. And then another thing that I want you to think about is can you actually save most of your commercial nitrogen application for in-season justification? So if we're able to do this, this actually maybe allows us to change our buying dynamics to some extent. So this requires obviously that you have a source locally for usually a liquid fertilizer because you want it to be highly available in season. So you've got to think about the buying dynamics here. But if you were to put off buying fertilizer until you absolutely needed it in season, what does that do for your P&L? What does that do for your input costs in your operation? And can you wait until you have a justification to actually use that fertilizer and mostly rely on mineralization? So these are some questions that I want you to consider and think about when it comes to how you're operating within your nutrient management plan and using justification. I want to make a quick note on analysis and records as well. Manure analysis is really important for properly characterizing it as a product. One of the advantages of sensors is that sensors don't care quite as much about analysis. We're really just reading the crop and reading what it tells us. But when we talk about modeling, models really care about the composition of the products that are being put into that model. So getting a manure analysis is really important for properly modeling how it is going to convert from that organic to inorganic fraction, as well as how those other nutrients like nitrogen are going to become available. Record keeping is also really, really important. So keeping track of those applications. Again, sensors don't care about this as much, but if you're starting to look at modeling, models really care about the records that are going in. They're going to use what you've told it you've done, and they're going to model out from that point. So record keeping is really, really important. It's important for performance. It's important for accurate recording at the end of the season, right? If you're going to do it in real time, it's going to increase the likelihood that it is accurate when you go back to look at it at the end of the season. And ultimately, it also connects the record of application to the justification for action. So if you have this documentation of what you did, the justification for the action, and you can show that it actually had the intended outcome, this is a really important thing to consider. The last thing that I'll note is that there are systems that are proliferating right now for manure rate control. Specifically, the John Deere Harvest Lab is a really cool technology that can sense manure analysis in real time and can be connected back to a rate controller to help eliminate some of the variability in manure applications. We are trying to work with the University of Nebraska on some research around this, their Eastern Nebraska Research and Extension Farm, to really show how manure can be managed variably as an input source. I promised that I would get back to the Georgia agronomic nitrogen rate definition for corn. And the reason why I want to get back to this at the end is there's still a lot of work to be done with these state level agronomic nitrogen rate recommendations to ensure that there's flexibility to operate and supply your crops with the nitrogen that they need agronomically. The Georgia definition does not currently allow for and specify much in the way of use of data to inform in-season changes. Everything that they do is based on soil tests and yield goals. And these two things are very difficult to use in-season data around. So if you are in the state of Georgia, you're in a state that currently doesn't have a lot of flexibility in terms of nitrogen management, I would talk to your extension agents and I would encourage them to pass up the chain the research that's being done in other states and the definitions in other states about how they're using justification for these nutrient management plans in season to ultimately get to a more agronomically appropriate nitrogen rate for the yield potential in the field. And lastly, as I wrap up here and hopefully save a little bit of time for questions, there are two other relevant things with sensing and modeling that I want to talk about. Obviously, I didn't talk about phosphorus at all, and some of you are probably sitting out there thinking, well, if we keep applying manure to supply nitrogen, we're going to keep putting phosphorus in the field. What are the limitations there within our nutrient management plan? Yes, that is a huge problem, and it needs to be addressed. I do think that there are some opportunities to leverage tissue testing, in this case, to isolate phosphorus as a yield limiting factor. There's also some early research in how we can use hyperspectral sensing and modeling to actually indicate phosphorus as well in season. So it's possible that we'll be able to work to a combined nitrogen and phosphorus system in season that can be used for justification, or at least showing that what we're doing on the nitrogen side is not getting us too far out of line when it comes to our nutrient management plan for phosphorus. Modeling is also an opportunity here as we continue to build out the efficacy of these models over time. And as data sets become larger, we do think we're going to get to the ability to deliver better preseason agronomic nitrogen rates. They still won't be perfect, but the hope is that these models can show enough efficacy that they can be a substitute for a university nitrogen recommendation for determining the agronomic nitrogen rate going into a nutrient management plan as well. So there is opportunity there as well. So with that, I know I threw a lot of information out at you. I hope it didn't overwhelm you or anything like that, but I would love to take any questions that you have around justification on in-season nitrogen management.
I've got a bunch of questions. So are you telling me that there is a device that will rate manure application according to the nitrification of a crop as it goes across the field? It will regulate the amount of manure on a device that will follow the map. Is that what you're telling me?
Yes, there is early indications, and this has been field tested, that you can actually use a Harvest Lab, plug in the analysis to a rate controller in the cab,
yeah,
and actually change the flow rate of manure out of the system. So yes, it's something that we are pursuing grant funding to demonstrate from a fully informed decision support system.
The second question, on the normal circumstance, how many days of real mineralization is there in a crop? If a crop's growing 180 days, how many days of actual mineralization? Because I saw that you mentioned it doesn't start until V6.
So let me go back to that, because I think that is an important question. I did not mean to communicate it that way, that it starts at V6. Mineralization is going on really as long as there is biological activity in the soil. If you're in an area where the soil freezes, right, that biological activity is going to be completely ceased, and so you're not going to get much mineralization when the crop is not actively growing or planted or shortly there before, right? In regions like we're in, you're going to get mineralization in some capacity almost the entire year. There will be certain days where biological activity is going to be slowed, but that's really part of why it's hard to build organic matter in southern soils, is that you have consistently high temperatures and that biological activity is ongoing. That's where, cover crops, manure utilization, all these other sorts of practices are necessary to build organic matter. So that mineralization is going on constantly as long as there's biological activity in the soil.
Can you tell me a little bit more about your nitrogen sensors that are in field? Can you elaborate on that a little bit?
For sure. So when we're talking about sensing nitrogen, the sensors that we use are all cameras that are mounted on satellites. So there actually is no hardware deployment in the field. There's no installation. This is completely reading crop reflectance that has made it through the atmosphere to the satellite to be collected with a camera. This can also be done with planes, with drones, really anything that has a camera mounted on it that is detecting crop reflectance. But that's how the sensors are working, is they're essentially picking up light in certain parts of the spectrum, measuring that light, and then we're able to correlate that back to the actual crop physiology itself, so biomass structure as well as light utilization.
If all that is the case, then why can't we get handheld devices that will read the nitrogen in a plant so we can go out in the field, instead of taking tissue samples, read that plant on hand so that I could go back and say, I'm going to adjust the rate at this field. I'm going to adjust the rate at that field.
And there are technologies out there that do that. So I would encourage you to look at Leaf Tech would be one of the technologies out there that's doing this. There are also SPAD meters out there that have been around for about 20 years at this point. There are Optrix sensors as well. This technology is actually, our technology is based on those handheld sensors and actually doing that through the field and basically demonstrating that crop reflectance can be used to inform nitrogen management. There's actually a study that was done in the 90s at the University of Nebraska that used these handheld sensors to go out and measure essentially in DVI or NDRE, right? And using that value determine whether or not fertigation needed to be applied to the crop. So there's some good backing towards that out there.
She's got you. We talked a little yesterday. Ooh, I'm loud. We talked a little yesterday about PSNT and tissue and overlaying that. Can you explain or show a little bit how that looks?
For sure. So if you, let's see, I'm gonna pull up a map here. I'm gonna start answering your question around soil moisture because that's one of the questions that we get a lot. We operate in irrigated agriculture a lot. Probes are being used at a very high rate in irrigated agriculture to inform irrigation applications, but they're only a single point location in the field. So they have limited utility for quantifying spatial variability, and that's really important when you're going to inform a full field irrigation decision. So that particular probe may just sit here, right, in the field because pre-season we thought that was gonna be the best place to put it, but it's really not in an area that's getting a lot of water ponding, doesn't have a very high leaching risk. When you think about pre-sidedress nitrate test, or you think about a tissue sample, it's very much the same, right? We're going out to a single point in the field that we think is representative of the entire area. We're going to pull that value, and then we're going to make a recommendation to the entire field based on that. The disadvantage, obviously, is that we're not getting all the information. The advantage is that we have a ground truth point, and with a soil sample or a tissue sample, you're not just able to assess and isolate nitrogen, you can also measure a bunch of other micronutrients and macronutrients. So if we think about calibrating, right, there are a lot of calibration techniques, geospatial calibration techniques that are starting to use single or a few point measurements in a field, correlate that to remote sensing data so that the remote sensing data can scale the information from one of those samples across the entire field. So really that's how I see this progressing over the course of time is yes, you may go out and pull a pre-sidedress nitrate test where you might pull a tissue sample, but that may ultimately get fed back into a system that matches it with the latest satellite imagery and propagates that information across the entire field with the confidence of a ground truth point.
Jackson, this audience may think this is theoretical, but this is a commercial application. Can you talk to some level of how many acres are being managed with this system without it going too much in your personal business?
Absolutely. So we got started in 2021. We started on roughly 8,000 acres that year. The last year that we did research at the University of Nebraska, I think we were on roughly 600 acres. So we had kind of a 10x scale up going into the first year of the business. Last year, roughly 70,000 acres used this technology to inform nitrogen management, and we're forecasting somewhere between 150 and 200,000 acres this coming year using the technology. About 80% of that is in Nebraska and surrounding states in the Corn Belt, but we are seeing some uptake in the Southeast at this point, just given the way that nitrogen is managed here. It is already managed in season because it has to be in a lot of cases, so there is some immediate applicability to our technology here.